Salam and welcome everyone. So today we're going to be working on the question on the screen that says, use the values of the relevant standard Gibbs energies of formation from the resource section to calculate the standard Gibbs energy of reaction at 298 Kelvin of the following reactions. The first reaction, and then we have another reaction. So I wanted to just quickly mention this. This is the B part. I've done the A part of this video. It is the physical chemistry Atkins textbook for anyone who is wondering. It's the 11th edition. So I want to quickly mention this. Looking at the question, we see that we've been told that we're supposed to use the resource section of our textbook to find the Gibbs energies of formation for the different molecules in this particular reaction and the second reaction as well. So we're supposed to have used those resource section information, the values there, to find the standard Gibbs energy of reaction. Now, to make your work easy and to make like tutoring you easy, I have decided to go on into the textbook and write out all of the Gibbs energy of formation values so that it's easier. So I advise you to pause this video now and to write all of this in your book that you're using while you're listening to this video. So now that you've written it, I am going to start explaining it. So generally, anytime that you're working with the Gibbs energy of reaction, you have to note that the general formula is the summation, okay, of the Gibbs energy of formation for the products, okay, minus the summation of the Gibbs energy of formation for the reactants. So you have to know this. This is such an important formula to memorize. So when you know this, then you'll be able to like start working. So you have this information right now. Now we have to like start with the reaction. So the first reaction that we're given is this one, zinc solid plus Cu2 plus would give us zinc 2 plus Cu solid. So I'm just going to rewrite it. Now, I'm not going to be going back and forth for each particular information. So make sure you pause it if there's anything you want to like have in your notes while I'm solving, because I already have my own notes and I'm going to be solving using my own notes. So you have zinc solid plus Cu2 plus aqueous. Then you have zinc 2 plus aqueous plus Cu solid. So we have this now. I'm going to be organizing this particular reaction based on the formula, general formula I just taught you. So the Gibbs energy of formation for this particular reaction is going to be focusing on the products first. So you have the Gibbs energy of formation for the products, okay? The first product, which is Zn2 plus, okay, aqueous, plus, don't forget we have a summation, right? The second product. So the Gibbs energy of formation for the second product, which is Cu solid. Okay, so all of that information minus, now we're going to deal with the reactant side. The Gibbs energy of formation, okay, for the reactants, the first reactant, which is ZNS or zinc solid, plus the Gibbs energy of formation for the second reactant, which is copper 2 plus, so Cu2 plus. So you can see that we've properly organized what we have. So now, of course, we're just going to substitute. So what we're going to be substituting is this information right here. Like we're going to be substituting for the first reaction, that is, we're going to be substituting each one of this information right here. So yeah, that's why I told you guys to write it so it's easier for you. So the Gibbs energy of formation for Zn2 plus, according to the resource section of the textbook that I've written earlier and I showed you earlier in the video, we have that to be negative 147.06 kilojoule per mole for Zn2 plus the Gibbs energy of formation for copper solid, we have that to just be 0 kilojoule per mole, or you can just say 0. So all of that information minus the Gibbs energy of formation for ZNS. So the zinc solid is just going to be 0. Okay. So the first product plus we're going to look for the Gibbs energy of formation for the second product, which is Zn2 plus. And looking at the research section of our textbook, we have 65.49 kilojoule per mole. Okay. So we just simply rewriting this, we just simply have 147 Gibbs energy of reaction is going to be negative 147.06 kilojoule per mole minus 65.49 kilojoule per mole. So the Gibbs energy of reaction is just going to be simply negative 147.06 minus 65.49. When you input that information in your calculator, you end up with negative 212.55 kilojoule per mole. Now, We're not done because, of course, we're dealing with chemistry, right? When we deal with chemistry questions, we know that we have to go back to the first information we have and look at the values. We see that the lowest number of decimal places that we have from the values that we use in our calculation, for this particular one, we have two decimal places. For this particular one, we have two decimal places, and as well, this one we have two decimal places. That means our answer has to be in two decimal places. And luckily for us, our answer is in two decimal places. So this is actually the answer to this question. Now we move on to the second reaction, which is just simply combustion of sucrose. So C12H22O11 solid, which is just basically here. This is sucrose for anyone who doesn't know. This is the chemical or the molecular formula for sucrose. So that's that. Plus O2 gas and plus 12O2 gas. So I'm rewriting what I showed you earlier. This is a combustion reaction of an organic compound. You're always gonna have carbon dioxide, okay, and water as the products. So balancing the equation. Actually, we're not really balancing, we're just repeating what we're given. Just looking at the equation, of course, is not balanced. So we have 12 CO2 here and we have 11 H2O here. So that is what was given to us, this reaction right here. So, of course, if you go back to what I taught you earlier, I'm just going to recap. The Gibbs energy of reaction is just simply the formation of the Gibbs energy of formation for all of the products, okay, minus the summation of the Gibbs energy of formation for all of the reactants. So you end up with the Gibbs energy of reaction is going to equal um, this one right here. So you have Gibbs energy of formation for the first products, you have that to be 12 CO2 gas plus Gibbs energy of formation of the second products, we have that to be 11 H2O liquid minus the Gibbs energy of formation for the reactant would just simply be energy of formation of the reactant would just simply be C12H22 or 11 solid. So that's that, the first reactant. Then the second reactant would be the Gibbs energy of formation of 12O2 gas. So that's how it's done. Now I want to quickly explain something to you guys. This formula here, the V here and the V here, is just for you to take into account the coefficients that could possibly be in a particular reaction. So for the products and for the reactant. So for example, now we see the coefficient of this particular first reactant is 1. The coefficient for O2 gas is 12. The coefficient of CO2 gas is 12. And the coefficient of H2O liquid is 11. So I'm going to just say that so that you guys understand that's what the V stands for. And even though we have properly organized this, we still have to do further organization because we have the coefficients present. So we have to rewrite this to look like this, right? So we're going to bring out 12 here. So it's going to be 12 times the Gibbs energy of formation for CO2. And the reason is because we cannot in any way, shape, or form have the Gibbs energy of formation for 12 CO2. That does not exist. We can only have the Gibbs energy of formation for a compound, not the coefficient times the compound, right? Just the compound. So we have to bring out the coefficient, in this case 12, and rearrange it that way before we can start to solve. So we have 11 here times Gibbs energy of formation for the compound, which is just H2O, okay, liquid. So all of that minus, do the same thing here. Here our Gibbs energy of formation is going to remain the same. Like this entire information will remain the same because we don't have a coefficient greater than 1 that we have to bring out. So it's just going to be this C12H22 or 11 solid. Plus, here we have a coefficient greater than 1. So we're going to say 12 times the Gibbs energy of formation for O2 gas. So that's basically it. So we have the Gibbs energy of reaction is just going to simply be 12 times Gibbs energy of formation for copper. I'm sorry, not for copper, for CO2, carbon dioxide gas. Is just based on what I have that I've written down from the resource section is 12 times negative 394 0.36, okay, kilojoule per mole. Okay, that's the first one, plus 11 times the Gibbs energy of formation for H2O liquid, which is just simply negative 237.13 kilojoule per mole. So that's the product side. And then you have minus Gibbs energy of formation for the sucrose, which is C12H22O11 solid. We have that to be negative 1543 kilojoule per mole. Okay. Plus the Gibbs energy of formation of O2, which is just 12 times the Gibbs energy of formation for O2. We see that to be 0 kilojoule per mole. So we have that information now. So we just simply, we just do the math, right? That's how it's done. So the Gibbs energy of reaction becomes 12 times negative 394.36 negative 4732.32 kilojoule per mole. Okay. Minus. So you have here, you've got plus and you've got minus here. So plus minus is just minus. So 11 times 237.13 is just simply 2608.43 kilojoule per mole. Of course, like I said, this is a product side. So then you have minus over here, okay, and then minus here, you're going to get plus. So I'm just going to say plus 1543 kilojoule per mole. So we have the Gibbs energy of reaction to equal negative 4732.32 kilojoule per mole minus 2608.43 kilojoule per mole. You're going to end up with negative 7340.75 kilojoule per mole plus 1543 kilojoule per mole. So continue. We just put this information on a calculator. Negative 4340.75 plus 1543 would give us negative 5797.75 kilojoule per mole. Now, I wanted to quickly mention something that this is like a really good time for us to note that in chemistry, we don't just leave our work just like this. Like, we don't just pick an answer whenever we calculate. We don't just find an answer whenever we calculate and just leave it like that. We have to make sure we put in the proper sig figs or proper decimal places. We see that the information that we have right from the beginning of our calculation is just this one, and this one. We can see the number of decimal places for this one is 2 decimal places. This one, 2 decimal places here. We don't see a point zero, but we know it's 1 decimal place. 1 decimal place because of math. If you say you have 5 is the same thing as 5.0. So we just assume it's a 1 decimal place situation. So we just end up here. So we have the Gibbs energy of reaction to be negative 5797.8 kilojoule per mole. And this is basically the answer to the second reaction. So now we've come to the end of this video. If you're a student who's watching this video and you're struggling, or you know someone who's struggling in school, I help students improve and succeed in all their STEM related courses, whether they're in middle school, high school, or college. I also help with student mentorship in order for them to properly navigate their academic life. So if you'd like to know more about my services, email me at shohabitutoring@gmail.com. I wish you guys all the very best. Make sure you like and subscribe. Assalamu alaikum wa rahmatullahi wa barakatuh.